Haven't sent it yet, Ryan. All right, so go ahead, work on the whiteboard. This is what you learned in yesterday's recording and assignment, the 4H assignment. All right, so I'll go ahead and the equation is up here. Let's go ahead and we'll annotate this together, and then I'll have you do the calculation. All right, so yesterday we learned about how to calculate concentration through an equation called molarity. All right, if you didn't see yesterday's lesson, make sure you go back and do that because that is really important. You need to be able to do this calculation on your own. So let's go ahead and we'll first annotate this together though. Let me go ahead and annotate this. All right, what is the molarity of a 2-liter solution with 3 moles of sodium chloride? 2 liters. Liters, is that the unit for moles or for volume? Go ahead, tell me in the chat box. Is liters the units for moles or volume? Oh yeah, Ryan, it is. It's in the announcements. It's in the grades tab. It was on the class plan, so it's all there. You should be able to find it for yesterday. So yeah, just go back and make sure you get it done. Thank you. All right, everybody in the chat box, again, I do need a response. What is this? Is this moles or volume? Moles or volume? Liters. What is liters? Think about a 2-liter bottle of Coke. Is that telling you the moles of Coke or the volume of the Coke? Oh, sorry about that, Ryan. Well, it's okay. You still have time. I haven't even zeroed it out yet, so you have some time. Yeah, awesome. So this is going to be our volume. Yep, this is the volume of our solution. And then 3 moles is obviously the moles of our solute, what's being dissolved, which in this case is going to be our sodium chloride. All right, so let's go ahead. You should be able to plug those in. So moles of solute divided by volume of solution. Tell me on the whiteboard or in the chat box, what is the molarity of the solution? You take the moles of solute and divide it by the volume of solution, the two things we just annotated and identified. So go ahead, I'll give you 30 seconds. I need answers from everybody either on the whiteboard or in the chat box. What is the molarity of the solution? Again, I do need to hear from everybody to let me know that you are here and ready to get started. All right, so putting a timer up on the board, need answers from everybody. 30 seconds, go, go, go. All right, I have 2 answers. That is not enough, so please give me your answer. Otherwise, I will start moving people to the check-in room because you need to be here. You need to be ready to participate. So again, take your 3 moles of NaCl and divide that by your 2 liters of solution and tell me what do we get for our molarity. I've seen Jalen participate so far. I've seen Annette and Christine and Ryan working, but I do need to see everyone else working. So I'm waiting on participation from Natalie, Melanie, Kayla. Participation, please, from Madison, Kevin, Jennifer. I have not yet heard from you in class. Gabe, Ayla, Anthony B. Have not yet heard from you. Thank you, Jalen. I see you in the chat box. Thank you, Kayla. Thank you. I see Anne Marie typing. Amy and Alex, I have not heard from you. So Alex, please get me your answer in the chat box. Yes, awesome. So if we go ahead and we enter this in, right, this is going to equal on the top, we have our 3 moles NaCl divided by, on the bottom, our 2 liters of solution, 2 liters. So capital L for liters, and 3 divided by 2 is going to give us 1.5. Now the units for this, remember, could either be mole per liter, so MOL over divided by L, so moles per liters, or you could also say 1.5 capital M for molar. Remember, this right here means molar. Again, that was in yesterday's lesson. If you haven't gotten a chance to do that, make sure you go back and do that. That way you are fully prepared for everything that we are doing in this unit. That's not rounded. 3 divided by 2 is just 1.5. I can go ahead and show you in a calculator. Give me a moment. Here we go. All right. Looking good. All right, calculator. Calculator. All right, so 3 divided by 5. Can you actually see my board? Can you see my board? It's all black. Okay. Yeah, make sure you tell me if the screen's ever all black so I can fix it, just so you know, because I've heard that issue a few times now. All right, yeah, so looking good. So you should be able to see my screen here. So 3 divided by 5, 3 divided by 5, or sorry, 3 divided by 2. Oh my gosh, 3 divided by 2, press enter, and the answer is 1.5. There's no rounding involved. 3 divided by 2 is just 1.5. All right, looking good, everybody. So that is our answer here, 1.5 moles per liter or 1.5 molar. How do we feel about that? Go ahead and give me a birthday cake if that calculation makes sense. Again, that was all from yesterday, all from yesterday. Thank you, Christine. Thank you, Annette. Beautiful, beautiful, beautiful. All right, so this is a reminder, class sessions are recorded and distributed for learning purposes listed here. As always, be respectful, appropriate, and participate. Please do not share contact or social media info for your own security reasons. We are on day 31 out of 60. We are officially over halfway through the through the trimester, which means that we are actually closer to the trimester ending than we were to the start of it. So again, make sure that you do yesterday's 4-H assignment using the 4-H recording, which goes over concentration and how you measure concentration using molarity. Today, we're going to go ahead and talk a little bit about solution chemistry, and we will be completing the 4I assignment as well as the 4I attendance. Okay, so today we're going to talk about solution chemistry. Sorry, that slide is incorrect. We're going to talk about solute solvent solutions, something you already know. We'll talk about the universal solvent, again, review of what you already know. We'll define dissociation and electrolytes and explain how metal ions move in galvanic cells. So these first two are reviewed. That should help give us a strong basis for these last two. Please go ahead and open up your 4I assignment. I'm going to go ahead and send that to you in the chat box. Green checks once you have that open. If I do not receive a green check from you, I'll go ahead and move you to the check-in room to make sure that you are ready to work. Green checks once you have your 4I assignment open and ready to go. I will give you 45 seconds. Go, go, go. Yes, it was mentioned, even if it's just opening, still give me a green check. That way I know that you're here and opening it up. Excellent. Waiting on green checks, please, Alex, Jalen, and Kevin. Jalen, I know that you're there, so please give me your green check. You were there just a few moments ago, so please give me your green check. Don't walk away from your computer. Kevin, green checks, please. Alex, green checks. Green checks, everybody, for opening up your 4I assignment. All right, looking good. We'll go ahead and check in with you and bring you back as soon as we get. All right, looking good, everybody. Let's go ahead and talk this over. So taking a look here, today we are going to go ahead and take a look at solutions a little bit more. So let me go ahead. I'm going to give you your whiteboard tools, and I want to know, a solute, is this what you have less or more of? And therefore, is it what does the dissolving or what gets dissolved? Take a look at the word solute. Remember, the word solute is a short word. It only has 6 letters. That's a hint for what it is. Go ahead and circle up on the board. Is it what we have less or more of? And therefore, is it what does the dissolving or what gets dissolved? Thank you. I see Annette, Ryan working. I see Christine working. Get your answers up there. Thank you. I see Amy on the board. Also want to hear from Anne Marie. Thank you. I see Annette on the board. I see Natalie working, Ayla working. Excellent job, everybody. Perfect. All right, let's go ahead and pause that for a moment and go over this. Yes, so the word solute is our shortest word, and remember that was our memory trick for remembering that this is what we have less of. It's the shortest word, so it's what you literally have less of. And you are definitely correct. If it's what we have less of, then it's what's getting dissolved. Great job. All right, let's go ahead and do the one on solvent. Go ahead and put that up there. Remember, solvent is our medium word. This is our medium word that has 7 letters, so it's a bit longer than solute. Go ahead and tell me, what is a solvent? Less or more? Does the dissolving? Gets dissolved. All right, perfect. Let me go ahead and pause those tools again, and let's take a look up here. Yes. Okay, Jalen, no problem. I'm going to go ahead and send you a link to tutoring, okay? And you can go ahead and sign up for that. Anyone else, please make sure you're checking your grades for the Unit 1 and 2 project. If you have not passed them, please go ahead and sign up for a tutoring time for next week. Okay, so make sure that you sign up for that. That's in the chat box. Thanks for reminding me about that, Jalen. All right, so let's go ahead and take a look here. So the solvent is the medium word. So yes, it's a longer word, which means it's what we have more of. And therefore, you are totally correct. It is what, in fact, does the dissolving. Sorry, let me erase this part to clean it up. So this is what is actually doing the dissolving. Now remember, once they get mixed together, they create a homogeneous mixture that is 8 letters long. Go ahead and write the answer on the board. What is that homogeneous mixture called? It looks a lot like our other words, except for this one has 8 letters. Go ahead and type that for me up on the board. Use your letter tool. Click on the board, and then you should be able to type and press enter to get your answer up there. Excellent. I see Annette up there. Let's get some more participation. Again, once you put a solute and a solvent together, mix them up. What is this thing on the right called, where they are mixed together and creating a homogeneous mixture? Homo meaning they look the same / uniform throughout. Oops. Throughout. Awesome. All right, get your participation up there. Waiting on participation from Amy, Anne Marie. Get your answers up there. Ayla, Anthony, Gabe, want to hear from you. Haven't heard from you yet. Jalen, get your answer up there. Jennifer, have not yet heard from you. On the board. Madison, Melanie, get your answers up on the board. What is this called? You have someone who has already answered the question, so you should be able to figure it out. Again, just write it so that you're reconfirming your own learning. Again, this helps to reinforce your own learning. You are the only person that is responsible for your own learning. Awesome. I see Ryan up there. I see Ayla up there. Great job, everybody. Yes. Thank you, Anne-Marie. This is going to be called a solution. Remember, solution is 8 letters long. So it's the overall mixture. Overall mixture. Thank you, Melanie. Thank you, Natalie. Great job, everybody. Excellent. All right, so that's our review right there. Again, solute is what we have less of, so it gets dissolved. Solvent is what we have more of, and so it does the dissolving. Together, they create a homogeneous mixture called a solution. This is number 1 in your notes. Please give me a green check when you have number 1 saved. You have 30 seconds to give me a green check for number 1. Spelling matters. Capitalization does not. Fill in the blank with the word solution. Go, go, go. All right, I'm waiting on green checks from Madison, Madison, Madison. Just you, green checks, please, Madison. Again, number 1, fill in the blank with the word solution. Capitalization does not matter, but spelling does. Perfect. Moving on, everybody. 100% green checks. Love it. All right, so that being said, water is the blank solvent. What type of solvent is water? It can dissolve the most things, right? It can't dissolve everything, but of the solvents that exist, it can dissolve the most, and therefore we call it the what. What do we call it? There's actually a hint on the board. Awesome. I see Annette in the chat box. Yes, this is called exactly. I see Christine typing. Get your answers in the chat box. What is this called? Perfect. Yes, it's called the universal solvents. Thank you. I see Natalie, you were typing it too. All right, so this is water is the universal solvent. It does in fact dissolve most substances, not all, but because it can dissolve the most in our universe, we therefore call it the universal solvent. Now the reason, all right, is because it has unique properties. Remember we talked about in a previous lesson, I think this was a video, but we also went over it in class as well, that H2O is made up of 2 hydrogens bonded with an oxygen. And what happens is oxygen is more electronegative, meaning it's greedier for electrons. So it pulls the electrons a little bit closer to it, making it slightly negative. Remember that this funky little Greek letter D here means partially. All right, so this means partially. It's not ionic. This is a covalent bond because they're still kind of sharing. All right, so covalent meaning they're sharing. Okay, but oxygen's a little bit more electronegative, making it partially negative, whereas the hydrogens are a little bit less electronegative. They're not as greedy. They don't hold on to the blanket of electrons quite as much, making them a little bit more positive, partially positive. All right, so the reason that this is called a polar covalent, again, you had a lesson that went over the difference between nonpolar and polar in a video. Make sure you go back to that lesson if you missed it. Polar meaning that they have different sides, right? So polar means that the sides are different. One side is partially positive and one side is partially negative. That's a quick review. Go ahead and give me a rainbow in the chat box if that makes sense. Rainbow in the chat box if that makes sense. Thank you, Christine. Thank you, Annette. Awesome. Thank you, Ayla, Melanie, Anne-Marie, Kevin on top of it. Great job. All right, let me go ahead and show you this link really quickly. And go ahead and drop this up on the board for us. All right, and what you can see here is that those partially positives and partially negatives of the water are really good at dissolving things because they can attract the different parts of a solute. So for example, you can see as this GIF goes, the negatives attract all the sodiums. The negative oxygens of water attract all the sodiums, and the partially positive hydrogens of water attract all of the chlorines and actually begin to tear apart the solute. All right, go ahead and give me a lightning bolt in the chat box if that makes sense. They are tearing apart the solute. Lightning bolt if you see that up there. So those partially negative oxygens pull at the positive sodiums because opposites attract. The partially positive hydrogens pull at the negative chlorines because opposites attract. Oh, let me go ahead and send you the direct link in the chat box. All right, so go ahead and click on that, Ryan, and then you can see that. I also do have a picture right here, though. All right, so, oh no, I don't have a picture right here. Maybe it's on the next slide? Yeah, it's on the next slide. All right, so again, what's happening here is those oxygens, which are slightly negative, actually pull apart at the positives of a solute, like in our example, positive sodium. And the partially positive hydrogens pull at the negative parts of a solute, like the partially negative chlorines. So here's an actual picture of it in case you didn't see the GIF. But you can see right here that these positive hydrogens are linking up with the negative chlorines. And right here, these slightly negative oxygens are linking up and pulling on these positive sodiums. So again, the reason they work so well is because of this partial positive, partial negative characteristic of water. All right? Awesome job, everybody. All right, so let's go ahead and talk a little bit about what's actually happening then in this process. This process is what is called dissociation. So dissociation occurs when ionic solids dissolve in water and they actually separate into their positives and negatives, just like we saw sodium being broken apart into its negative chlorines and its positive sodiums. They are separating into positive cations, negative anions. Go ahead, give me give me some money in the chat box if you see that. So sodium chloride dissociates, separates into positive sodiums, negative chlorines in water because of how water dissolves it. Excellent. Now, on the other hand, non-ionic solids, which we talked about those being covalent, so covalent bonds do not dissociate because covalent bonds don't have ions in them, right? We talked about how ionic solids have ions, positives and negatives. Covalents don't have ions. They only share their electrons. So for example, sugar is a covalent bond. And so since it has no positives or negatives, it can still dissolve for a different reason, but it's not dissolving because it's being pulled apart by water. All right, let's go ahead and take a look at a demo of this. And I will go ahead and I will put this in the chat box as well in case you would like to participate. All right, here's the link in the chat box if you would like to download it. This one is one that we actually need to download. So I'll get it open in a moment. I don't know why it's not opening. Okay, here we go. Let me go ahead and share this with you up on the board. And here's our desktop. Cool beans. All right, let's go ahead and take a look at this. So what we can see up here is that we have, what we can see right here is we have a liquid down here or we have water down here that we're going to go ahead and dissolve stuff into versus what we can see up here. So let's take a look here. So when I add salt, for example, and I'm going to put a conductivity tester in here. Okay, so salt is actually breaking apart into positives and negatives. And this conductivity tester proves this because positives and negatives allow electricity to flow. So if we were to take a look at this at a micro level, all right, and put in some sodium chloride, you can actually see that the water breaks apart the sodiums and chlorines into their ions. Go ahead and give me a smiley face in the chat box if you see that, if that makes sense. Smiley faces if you see that and that makes sense in the chat box. Excellent, Annette. Thank you, Jennifer. So they're breaking up into their individual ions, On the other hand, if I add sucrose or sugar, okay, you can see that sucrose or sugar does not break apart into its individual ions. It has no ions to do so. Sucrose just stays as sucrose molecules. One more time, go ahead and give me a music note in the chat box if that makes sense. I see Annette and Jennifer participating. Let's get some more participation in that chat box. Thank you, Christine. Thank you, Annette. Awesome. So again, salt is ionic, so it breaks apart into its separate ions. Sugar is covalent. It has no ions, and so it cannot separate into separate ions. Awesome. Now, that being said, again, if we add salt to a solution, this makes the light grow brighter and brighter because it has ions to carry electricity. Sugar, on the other hand, if I go ahead and I reset this, and I put the conductivity tester in. Sugar, on the other hand, if I add a bunch of sugar, sugar is not breaking apart into positive or negative ions. It doesn't have them. It's not an ionic bond, and therefore there is no change in the electricity in the water. All right, excellent job, everybody. Let me go ahead and jump back over here. Perfect. Okay, so this is number 2 in your notes. Go ahead and give me a green check when you have it saved. Number 2, sugar is a covalent molecule with no positive or negative ions. Go ahead and fill in the blank with the word covalent and give me a green check. Go, go, go. 30 seconds. Spelling matters, capitalization does not. 10 seconds remaining. Green checks, please. Kevin, Kyrie, and Melanie. And I will send the links in the chat box again if you need them. Awesome. Okay, sorry, I did want to mention there's one more I wanted to show you right here. All right, so right here, one more thing that you can see is if I put in salt, again, you can see it immediately begins to tear apart the sodiums and chlorines, versus if you put in sugar, the particles all stay together. The molecule stays together. Awesome. All right, so sorry, I wanted to show that to you too. Cool. All right, everybody, let's go ahead and take a look at now what we're going to talk about, electrolytes. How many of you have ever heard the term electrolytes? Probably having to do with sports drinks. Go ahead and give me a bat if you have ever heard this term, electrolytes. For example, if you've ever seen like a Nike commercial with like the like weird, no, sorry, not Nike, up, is it a Powerade? Gatorade commercial with like the colored sweat coming off of them, those old commercials. I don't know if you watch commercials anymore. Yeah, all right. So electrolytes, you often hear in terms of sports drinks, but you need to understand why are electrolytes important to you as a person. So remember, electrolytes, we were just talking about ions. Electrolytes are defined as ions in solution that can carry electrical current. Just like we just saw with our sugar and salt solutions, that salt allows you to carry electrical current through water. That's why the light lit up. Now, this brings us to this idea of blood, plasma, and interstitial fluid. So all the parts of your body have cells, which is interstitial fluid is between your cells. All of these parts have electrolytes, most of which are sodium. So you actually eat salt quite frequently, not because it's tasty, but because you need these sodium ions. Now, the reason is because electrolytes are essential for your body's nerves, heart, and muscles, because your nerves, hearts, and muscles are all powered by electricity. Right? So that's why electricity can hurt us, because it gives us too much electricity. If you get struck by lightning, for example, and it overwhelms your electrical processes in your body. So you as a person are powered by electricity. You are an electrical being. So you need electrolytes. Go ahead in the chat box, give me a soccer ball if that makes sense. Soccer ball if you understand. Just want to make sure everyone's following along. Perfect, Christine. Thank you. Annette, ouch. Thank you. Soccer ball if you're following along so far. Thank you, Ryan. Thank you, Natalie, Kayla, Melanie. Awesome, Amy, Jennifer. Cool. Now, the problem is when you get dehydrated, you actually lose electrolytes, right? Which is what these sports drinks are doing. They are trying to give you more electrolytes. Go ahead and tell me in the chat box really quick, which one do you prefer? Do you prefer A for Gatorade or B for Powerade? Which one do you prefer? Awesome, I see Christine, Annette. Amy, all right. Looks like most of us are saying that you prefer Gatorade. Gotcha. Cool. Now, this is important because, for example, if you are to run a marathon, marathoners cannot drink solely water when they are running. The reason is because when they run and they sweat, your sweat is salty, so you are losing electrolytes. If they only replenish with plain water, they can actually die from lack of electrolytes, which is why some people can actually collapse and die during a marathon because they lose too many electrolytes, they have too much water, the water is too dilute and doesn't contain salt and sugar, and therefore they don't have the energy from the sugar and they don't have the electrolytes from the salt to carry electrical impulses. So it's really important that when you're working out really, really hard, you do need to have electrolytes replenished. All right, so let's go ahead and take a look here. I'm going to go ahead and put the whiteboard tools up on the board. All right, and I want to know which of these is the solute, the solvent, what does a water molecule do? What is dissociation? And what is the purpose of electrolytes? Go ahead and match those up for me on the whiteboard, and I will take a look at who is participating. Go, go, go. Excellent. I see Ayla on the board, Christine on the board. I see Annette, Amy working, Jennifer, Ryan working hard up there, Natalie, thank you. Melanie on the board. Let's get some participation, please, from Anthony. Anthony, please participate up on the board. Let's get some participation, please, from, who else am I missing? Gabe. Gabe, go ahead, participate up on the board, please. Thank you. I see Jalen working up there. Let's get some participation from Jennifer, or sorry, no, Jennifer's up there. Who else am I missing? Kevin, Kyrie, get your answers up there. Thank you. All right, looks like we have most people. Jose, looks like you just joined us, so I'm going to go ahead and send out the links to you. Cool. All right, everyone. I'm going to go ahead and pause those tools. Sorry if you didn't get a chance to finish, but I do want to confirm our answers here. So taking a look here, solute, I'm going to use red. Yes, solute is what gets dissolved. This is what we have less of, and that should make sense because solute is the short word. So that's our memory trick for reminding us that we have less of that. Solvent is what we have more of, and therefore it's what's doing the dissolving. Again, it's a slightly longer word. A molecule, water molecule, yes, water molecule is unique. It has a slightly positive oxygen and a slightly negative hydrogen, which allows it to tear apart things the best of all the solvents, making it what is called the universal solvent. Taking a look right here, dissociation. Yes, this is when ionic solids break apart into cations and anions. Do covalent bonds dissociate? Do covalent bonds like sugar dissociate? Yes or no? Tell me in the chat box. Do covalent bonds like sugar dissociate? Yes or no? Covalent. Remember, if dissociation requires you to be an ionic solid, do covalent bonds dissociate? No, because they're not ionic. Exactly. So covalent bonds, covalent solids, do not dissociate. Dissociate because they don't have ions. It's literally in their name. They are not ionic, okay? And remember, this is like sugar, and that is why sugar cannot carry electricity. So sugar cannot carry electricity, something that we saw something that we saw in our demo today, okay? And then electrolytes, we are correct. Electrolytes are ions in solution that help to carry electrical current and are very important for our bodies. No worries, that's why we want to make sure that we check all of these answers and go over them. This is number 3. Go ahead and give me a green check when you have this saved. You have 45 seconds to work on number 3. Answers are on the board. Answers are being provided. Green checks, go, go, go. All right, waiting on green checks, please, from Jose, Kyrie, and Melanie. Jose, Kyrie, and Melanie, green checks, please. If we don't get your green checks, we'll go ahead and move you to the check-in room. Is that Melanie? Melanie, I've seen your participation, so you're good. Jose, Kyrie, just waiting on you two. Have not seen you participate. I need your green checks, please. Thank you, Jose. Perfect. Kyrie, still waiting on you. Green checks for number 3. All right, everybody. All right, so the next thing I want to talk about is metal cations. So remember we kind of already talked about this in a previous unit that metals have only a few electrons. So when they bond, if you only have a few electrons, is it easier to gain a bunch more or to lose the few that you have? Tell me in the chat box. Remember we have the Octet Rule, so most atoms want 8 electrons. Remember, that's our octet rule that we learned about in the last unit. So metals, do they want to gain 5 to 7 more, or do they want to lose 1 to 3? Which one is easier? Gaining more or losing the ones that they have? Gaining or losing, which one's easier? Yeah, they only have a few electrons, right? So they only have a few. Only have a few, and so it's much easier for them to lose electrons. They want to lose their electrons. All right, so what that brings us to is that when an ionic solid dissolves, remember ionic solids have ions, which means that they also include metal ions. When they dissolve and dissociate, you end up with positive metal cations because as they lose electrons, they actually become more positive, becoming cations because remember electrons are negatively charged. So if you lose negativity, you actually become more positive. So you end up with positive metal cations in solution. And the cool part about metal cations is metal cations are actually quite colorful. So you can take a look here at some different examples at the top and at the bottom. So at the top, these ones are pretty colorful: titanium, vanadium, chromium, manganese, iron, cobalt, nickel, and copper. All of these produce these beautiful colors when they dissolve in solution as ionic solids. And here are some real examples down here. Take a look here at copper and iron, cobalt, and nickel. Tell me in the chat box, which of these is your favorite color? Tell me which one is producing your favorite color in the chat box. Tell me which one do you like. Awesome. I see Jose typing. Yeah, cobalt. Yeah, cobalt's a pretty cool one. So this one right here is cobalt. Anyone else, which one do you like? Go ahead, tell me in the chat box. Yeah, you can see both the picture as well as this example. This one's just kind of dilute in the real example. Cool. All right, everybody. So let's go ahead and talk about this. This is number 4. Go ahead and fill in the blank with the word lose and give me a green check. You only have 20 seconds to do this. Capitalization does not matter, but spelling does. This is a fast one. 20 seconds to do number 4. All right, to Anthony, Jose, green checks for number 4. Thank you, Jose. Anthony B, green check, please, for number 4. Anthony B. All right, let me know if you need help, but I'm going to go ahead and move on. If you missed it, it'll be in the recording. All right, so the last subject we need to talk about is galvanic cells, because galvanic cells are also related to ions in solution. That's a big topic for today. So a galvanic cell is also known as a chemical battery. How many of you, for example, have ever had a really old battery in something in your house, and when you open it up, it was all crusty? How many of you have ever had that happen? Tell me in the chat box. When you open up some electronic and the batteries are all crusty. Yep, Ryan. Ayla, you have as well. Let's see here. Who else has had that? Tell me in the chat box. Yep, definitely, Annette. All right, cool. So this is important to understand because batteries are, as evidenced by the fact that they get all crusty when they get old, have chemicals inside of them. So a galvanic cell is another word for a battery that you might use at home. So galvanic cells actually show how ions in solution can carry electric current. They take advantage of this idea of ions in solution that we've been talking about throughout this lesson. So let's take a look down here. We're going to go ahead and start over here on the left, all right, and we will end over here on the right. So on the left, what you can see is zinc is a metal, and zinc is solid, and it begins to dissolve inside of a nitrate solution. As it begins to dissolve, you can see here that it's releasing positive zinc ions. So you can see right here that positive zincs begin to come off of it. But in order for positive zincs to be coming off of this, it needs to be losing the same amount of opposite electrons. So it's going to begin to lose negative electrons, and those negative electrons are actually going to travel over through the top to the right-hand side. And remember, moving charges are electricity. So these moving charges, that is electricity. So as these electrons move, you are creating electricity, and the light turns on, or your phone turns on, or your remote control turns on. All right, so that is how batteries work. Now, as those electrons move over to the other side has copper 2+ ions in solution. So the other side does have ions in it. So Cu2+. Cu2+, and where on the left-hand side, zinc was actually losing its electrons, on the right-hand side, as these electrons come in, they pair back up with a copper ion to go back in and turn into solid copper. So this time, the copper ions go back in. So you can see here, we start off with solid zinc, it dissolves and loses both electrons and positive zinc ions. You have to have equal amounts of both in order for this to work, because you can't have unbalanced amounts of this, okay? As those electrons flow from the zinc side to the copper side, they produce electric current, turning on your light or whatever else you're using your battery for. On the right-hand side, the copper 2+ ions gain those same electrons, reform back together into solid copper on the right. So as time goes on, you can see right here, the zinc begins to dissolve and the copper begins to grow. Go ahead in the chat box, give me a lightning bolt if this process is beginning to make sense. You should be able to follow from left to right what is happening. Should be able to follow from left to right what is happening. Perfect. All right, let's go ahead and actually see how we're doing here. So you can see this right here. Again, the zinc is going to lose zinc ions and release electrons that move over to the copper side, that then hook up with the copper ions and create more positive or more solid copper. And this is a battery, right? So we're using chemicals to actually create electricity and create, and this is how a battery works. All right, cool. So let's go ahead and take a look here. We're going to start off with how solid zinc dissolves in solution. Tell me in the chat box or point for me on the board, what do you think is going to be the next step? If we start with solid zinc, what happens next? Do the electrons travel from left to right? Do the copper ions gain electrons, or do the zinc ions get formed and electrons are released or lost? What do you think is the next step? Go ahead and point for me on the board. We're going to work on this one together. Use your pointer tool. That's this tool right here. Please work quickly. We're almost out of time, or we are out of time, so please work quickly. I need for you to point for me on the board. The faster you participate, the faster we get done with class, and the more you learn. Again, just follow the diagram. What's happening? Do we first do electrons first travel from left to right? So that's this part up here. Do zinc ions get formed, or do electrons get lost and electrons are lost? Or do copper ions gain electrons from solution? What comes first? Awesome. I see Ayla on the board. I see Ryan on the board. I see, awesome. Get some more participation up there. I see Annette on the board. Perfect. Amy on the board. Awesome. I see some people finishing it. I love it. Great job. Yeah, so exactly. So if you start off with zinc, you then have to make the zinc ions. Perfect. From there, we saw that the middle step is we create electricity. So those electrons travel and move over to the right. At that point, you now have the copper that begins to reform. So the copper ions gain those electrons. And finally, you end up with more solid copper. Awesome. All right, let me go ahead and take a look at this and confirm this. So again, we start out with solid zinc dissolving. The zinc ions are formed and electrons are lost. Those same electrons travel through the wire to turn on your light and cause electricity. Again, we have a chemical battery creating electricity. On the right-hand side, those copper 2+ ions hook up with the electrons, and as they get together, they form solid copper. Awesome. This is number 5. Go ahead and give me a green check when you have this saved. This is an ordering one, so step 1, step 2, step 3, step 4, step 5. It is written for you up on the board. I will give you 45 seconds since it's slightly longer. 45 seconds to do number 5. Here we go. All right, 15 seconds. We'll go over attendance in just a moment. Remember, you cannot get attendance unless you do the attendance work sample at the end, the discussion. Green checks Anthony, Jalen, Kevin, Madison, Ryan. Perfect, just waiting on Anthony B and Madison. Anthony, green checks for number 5. Thank you, Madison. Anthony, green checks for number 5. Perfect. Thank you, everybody. All right, so make sure you submit that and then tell me in the chat box, how did we do today? We should have gotten 100%. It was a lot of information, so we did each question together. How did we do? Tell me in the chat box. Awesome, Ayla, Christine, great job. There we go. Awesome, Ryan. If you didn't do well on it, remember you can always retake it. Recording will be uploaded around 1 to 2 p.m. So we talked about solute solvent solution, the universal solvent, dissociation, and electrolytes, and how metal ions move in galvanic cells. Today was all about how ions in solution begin to work. All right, let's go ahead for today's attendance. Oops, sorry, hold on. Sorry, this is incorrect. Give me a second. Okay, what is the substance that does the dissolving called? Go ahead, tell me in the chat box. What is the substance that does the dissolving called? Again, this is kind of a review, but want to make sure that we are understanding this. Yes, exactly. So solvent, remember, is the slightly longer word. So that's the one that actually does the dissolving. Great job, everybody. That is the answer for today's attendance discussion. Please actually write it out. So say the solvent. Oops, let me write it up on the board for us. The solvent does the dissolving. That is the correct answer for today's attendance. I'm going to go ahead and send you the link in the chat box, and then you are dismissed, and I hope you have an excellent weekend. See you all later. All right, go ahead, take a minute to do that, and then I will begin to log people out if you haven't logged out already. So this right here is the correct answer. The solvent does the dissolving. Thank you so much, everyone, and we will see you later. Bye, everyone. Recording.